Okay, welcome back, everyone. We're going to move on next to the distributions module, and Dimitris Giovannis will present the distributions module, and from there we will transition to the sample methods module. So give me one moment while I transition to Dimitris.
All right, good morning from me also. I'm going to discuss about distributions module, one of the most important modules in UQpy, since it's involved in all other, almost in all other modules. With the distribution module, you can define basically a random variable. You can find its distribution structure, which means that you can do all the related operations that are defined in UQpy. So basically what you can define in with a distribution module is you can define probability density functions, cumulative distribution functions, as well as their inverses, moments, logarithms of the probability densities, as well as parameter estimates for generic data for common distribution types. One can import the distributions module by using the following command from UQpy, just import distributions. Now the distributions module contains basically three classes. We have the distribution class, which is the parent class of the module, and also we have the subdistribution class and the copula class that are called within the distribution class. Now, using the distribution class, one can define different types of distribution. Currently, in UQpy, we can define marginal distributions for single random variables. We can also define joint distributions for independent random variables, as well as joint distribution for dependent random variables. Also, as I will discuss later, one can define custom distributions. Now, the distribution class has the following attributes. In order to be able to define a distribution object, what you need to define is, first of all, the name of the distribution. So the attribute dist name basically is used in order to define the name of the distribution for each random variable. So this can be either a string, which means that you have one random variable, that's the univariate case, or this can be a string, a list of strings, which in this case means you have a multivariate distribution. This attribute is required, and without it, there's no way to build the distribution object. Also, there's another attribute that's called the copula, which defines the dependence between the random variable. This is an optional attribute, and it's not required if you have independent random variables. And in order to define the copula, you need to provide a string. Now, for both of these attributes, there's no default distribution. There's no default value, a default name. So this must be defined by the user. Now, in order to be able to instantiate a distribution object, so if you have a univariate case, which means you have one random variable, all you have to do is type distribution and then provide the name of the distribution. Now, in this case here, where you have a single name, which this is a string, basically, you define one random variable. Now, if you have more than one random variables, you mean you have a random vector, and these random variables are all independent. In order to be able to instantiate a distribution object of this random vector, you need to provide the names of each distribution, the name of each distribution within a list. Now, the other case where you have a random vector, but there's some kind of dependence between the random variables, again, the way to define this distribution is by giving and providing a list with the names of each random variable, but also providing the copula. Now, available distributions in UQpy are basically, we have 19 distribution types according to SciPy stats. We have beta, binomial, Cauchy, Laplace, some of them. And also we have the case where you can define, the user can define its own distribution. Now, in this table here, you can see that for each distribution, we have a short name so that it can be used within the UQpy. So, for example, if one wants to use the inverse Gaussian distribution, you need to write the name inf_Gauss in UQpy, so for it to understand that we're dealing with the inverse Gaussian distribution. Now, currently, regarding the copulas, the only available copula is the Gamble copula, and more specifically the probability density function of the Campbell copula, but it's intended in the future to add more copulas. So basically, you have the parent distribution class, and you have the subdistribution, which is called by the distribution class. This class is built according to the library of the statistical functions of SciPy stats. This means that when you define an object of type distribution, this enables you to have different functions. This means that we can have the PDF, the probability density function, the cumulative distribution function. You can generate random variables from this distribution. You can calculate the inverse cumulative distribution function. You can fit the parameters of a distribution to some data, or you can estimate the moments of this distribution. So basically, what you need to have in mind, what someone needs to have in mind, that is, in order to be able the distribution object, you need to know how SciPy stats is calling a distribution function. So in case someone wants to calculate, to generate random variables according to some distribution, this can be easily done in UQpy by defining a distribution object where you provide the name of the distribution as a string, and then you get the attribute, and then you call the function RVEs of the distribution, which basically takes as input parameters the parameters that SciPy uses. So basically, this part here, the second part where you have .rves, .pdf, CDF, is the same as SciPy stats. So what's the advantage of using UQpy in order to define distributions and not directly using SciPy stats is that this way you have an object that has all the input attributes gathered together of the distribution. So basically, that was the univariate. When you have one random variable, this is straightforward. You just provide the name of the distribution and the function that you want to estimate, for example, the logarithm of the PDF, the way the SciPy stats is using is calculated. However, when you have more than one random variable, which means that you have a random vector, again, you provide a list with the names of each random variable, and again, you estimate the function you want based on SciPy stats. But for example, in the probability density function, since no copula is provided, it means that we have independent random variables, which means that the result that we're getting, it's the product of its value of the PDF for each random variable. So basically using the distribution function in UQpy is pretty straightforward, and it will enhance the sampling methods that we're going to describe next. So a few words about the copula. Basically, the copula is used in order to describe the dependence between random variables. And it's basically a multivariate probability distribution function that has a uniform probability distribution for each random variable. So in order to define the copula class, all you need to provide, the user needs to provide the copula name, which is a string, and the distribution name, which is basically implicitly provided into the distribution class. So currently, for the copula class, the available options are the Campbell copula, but as I mentioned previously, in the future release, we're going to add more copulas. And currently, we only have the probability density function of the copula. Now, one of the most important aspects of the distribution class is that besides the already known distributions that can be also found in the SciPy stats, UQpy provides the user to define its own distribution name with its own name. So, for example, the way to do that is by creating a Python script with any name, and within that script, define the functions that are required, for example, the PDF, the CDF, the ICDF, in accordance to SciPy stats in order to be able to use them. This way, UQpy will understand that the PDF of the distribution function is given by this function within this script. So this will enhance the user to be able to describe it, to define its own PDF and not limit it by the options are available in SciPy stats. So basically, to recap this, using the distribution function is very easy in UQpy. The only thing the user needs to provide is the name of the distribution. This way you can build a distribution object, and then this object has all the attributes, all the functions that SciPy stats provides. So in order to calculate the required function, all you need to do is define, provide the parameters and the required parameters for each function. An example of the distribution function can be found within the example folder, more specifically in the distribution. So here, in the distribution folder, we have the distribution example, the Jupyter notebook. So in this case, we are going to show how to define and use one of the univariate distributions that are supported by UQpy, how to define a custom distribution, and how to define a multivariate distribution, giving first of all a list of independent marginal distribution, and giving a list of marginals and a copula just to showcase the difference in the dependence of the structure. So first of all, in order to be able to use the distribution function, one needs to import the necessary libraries. And in order to do that, from the first line is that you need to import from the module UQpy distributions. This is the module. You need to import the class distribution. Now here also we have imported some necessary functions in order to run this example, like matplotlib, which is used in order to do all the plots. Now the first case, we're going to define the univariate log normal distribution and call this object in order to calculate its PDF, its CDF, and other methods. So basically, you define the object dist by defining the distribution, by calling distribution and providing at distribution name a string that has the name that you want, log normal. So in this case here, if we run this, we see that we have defined an object, and the attribute, this name of the object, corresponds to the one that we have provided. Now here, we can now plot, we can use this object in order to plot, in order to estimate the PDF and the logarithm of the PDF of that distribution. This is done by calling from this object here, dist, the function PDF, and providing the parameters of the distribution we want. Now, here X are the values at which we want to estimate the values of the probability density function. These are given by this vector here. While the parameters, these are the parameters of that correspond to the log normal distribution that we want to calculate. So here you can see we have estimated, we have calculated the probability density function of the log normal distribution, as well as the inverse, as well as the log normal, the PDF and the log norm and the logarithm of the PDF. Also, we can estimate, we can use that distribution object to calculate the moments of that distribution. So we are again using the object dist that corresponds to the distribution that we've built, and we are calling now the moments function, and by providing the parameters of the distribution. Now, as you can see, this part here where you call the moments and you provide the parameters is exactly the same way that SciPy stats is using this method. So you see here that we can have estimated the mean, the variance, the skewness, and the kurtosis of the distribution. Another example, for example, we can use the method random variables to generate random variables from this distribution. Again, all we need to have is the object distribution that we have defined in the beginning of the script here. Basically, all we have to do is create this distribution object here, and then we can call this object with the method random variables, and the way that SciPy stats is using it by providing the parameters and the number of samples, we can generate random variables based on that. And here we can also see the results by using the fit function, where we have some data and we can fit the parameters. Now, as I mentioned before, UQpy provides the capability of defining your own distribution function. So, for example, we have this function here defined in a Python script that it's called Rosenberg.py, where here you can see we have defined the methods for the Rosenberg bivariate distribution, and we define basically the PDF and the log PDF of that distribution in a way according to SciPy stats again. Now, since we haven't defined the fit moment, the fit, or the RVEs, or any one of the other function, this means that we cannot estimate them. We can only estimate the PDF and the log PDF of the Rosenberg function. So by providing this, you see that we have initiated the object distribution that corresponds to the Rosenberg function, and then we have used the method of PDF in order to be able to calculate the PDF of this function. As you can see here, as I mentioned before, since we haven't defined in the script, in the Python script, the fit function or the RVEs function, if we try to run these methods, we will get an error that says that the method fit is not defined. Now, another example is this one, where we have not a univariate function distribution, but we have a vector of distributions. We have two random variables. One is a normal random variable, the second one is a log-normal random variable. You see, we have defined the parameters of the distribution. Basically, we have a list of which each entry, it's a list or an array defining the parameters of its distribution. So again, after initiating this object here, we can use it in order to estimate the PDF of the random vector. So here you see that we have two random variables that have, the one has the normal distribution, the other one has a normal distribution. Now, so far, we have discussed about the case where we have independent random variables. However, with UQpy, we have the capability of adding some dependence to the random variables. And this can be done by using the Copula class. So in this case, I'm going to show you two examples where in the first case we have independent random variable, but in the second case, we have a copula. So this is the first object where we define a distribution of two random variables. In this case, where we don't define the copula, we have independent random variables, we have two independent random variables. While in the second case here, with the object dist_2, again, we have the same two random variables, but in this case, we have added dependence between the two random variables, according to the Gamble copula. So if we are to compare these two distributions, we see here the PDF, that in the first case, this is the PDF, this is the basic counter plot of the PDF of the two independent random variables, while in the second case, again, we have the counter plot of the PDF, where we have the two random variables, but they are with some type of dependence between their marginal distributions. So you see that by having this, again, here we can see the result of, we have plots of the CDFs of the independent random variables, as well as the dependent random variables. So you see by using with UQpy, it's defining a distribution object, defining a random variable, which means defining a distribution for this random variable, and using this distribution in order to calculate different moments, different functions of these random variables is straightforward. But what is more important is that the user can define its own random variable, basically its own distribution type, and use it according to its problems. Also, what is very necessary is that we have that with UQpy, with the distribution modules, one have the opportunity to provide dependence between the random variables using the copula. So using the distribution modules is very important in UQpy, and it's required if one wants to use the sample methods or the inference models. Basically, if one wants to use UQpy Distribution modules is very important in order to be able to define the random variables that are going to be used across different methods.